This is a first part of what I would call like a practical guide to biomechanics terms, physics, mechanics, engineering in general. Here's the idea. The idea is that as a golf teaching professional, a coach, a trainer, whatever it might be for any sport, obviously we're focused on golf here, but really for any sport, you're not a physicist, you don't want to be a physicist, you're not an engineer, you're a coach, you're a trainer, you're a medical professional, but you need to understand the concepts enough, the sort of the laws and the concepts that govern motion from a physics and a sort of biomechanics perspective in order to better understand performance, better understand injury, to better apply this information in terms of coaching and in terms of training and in terms of therapy. Okay, so we're going to start really with understanding lower body mechanics and swing patterns, and that's kind of where we started with this hammer throw concept, and this is going to be fairly general. I wanted to point out just some basic stuff about force. Okay, so we're going to talk about Newton's laws, three areas. And I'm just going to read this off the thing. The first law, when viewed in an inertial reference, don't worry about that, an object either remains at rest or moves at a constant velocity unless acted on by an external force. Okay? So that just means an object at rest tends to stay at rest, an object at motion, a constant velocity, tends to stay in that constant velocity or that momentum. In other words, a force applied to an object impacts its momentum. So very simply, force equals mass times acceleration. Acceleration essentially boils down to a change in velocity, or in the case of, say, your weight when you stand on a scale, gravity. So it's just understanding that force is a measurement of the mass of an object times the acceleration, and the acceleration boils down to the change in velocity. Change in velocity can be from 0 at rest to something, or it can be a steady state velocity that's either decelerated or accelerated, or increased or decreased. So very, very straightforward. The second law is that the vector sum of the forces on an object is equal to the mass multiplied by the acceleration. In other words, what this is basically saying is that force has not only magnitude, but it has direction. Force is a resultant force. A resultant force means it's composed of directional components as well as magnitude. So we can tell something about force with respect to how much, the magnitude of it, as well as the direction of the applied force. These are going to be important basic concepts to understand when we start to discuss our interaction with the ground and the ground's reaction with us and using force to produce movement. The last one is that when a body exerts a force on a second body, simultaneously, or I'm sorry, when one body exerts a force on a second body, the second body simultaneously exerts the force in equal magnitude but in opposite direction. So we want to understand the resultant concept in terms of not only magnitude of force but direction of force, so that we can understand when we apply a force into a second body, second object, the equal amount of force as well as the exact opposite direction is then applied back to us. And we're going to use that when we interact with the ground. So we're going to apply force into the ground, not only with magnitude, but with direction. And the ground is going to reply by sending that force back, not only the magnitude, but in the direction equal and opposite of the direction we applied that force into the ground. That stuff is super important to understand the basic concepts of what's going on. So try not to get too technical with this. We're trying to provide it in terms and provide it in concepts and visualizations that make sense to you on just an intuitive level, something that you can distill down from data and technical data into information that's usable. Okay? So the last thing I'll do, hopefully you can see this on the board, is kind of just give you an idea of how forces are being applied into the ground then. Okay? So here's our golfer, he's standing, or our athlete is standing, okay? Here's the flat surface of the ground. So let's look at the components that make up the direction of applied force. You have one component, if we look at this in terms of 3 dimension, you have one component that is essentially perpendicular to the surface you're standing on. And we call those vertical forces, but really what they are normal forces, normal meaning perpendicular to the surface you're standing on, okay? You then have forces along the surface. So if we're looking at this face on, you'll see there's a directional here along the surface. We'll call that X. So we'll call our downward Y. We'll call this X. And then if we were to look at the surface essentially down through our feet, okay, so now we have X going, let's say I'm standing like this. I have X going along the surface here. I'm going to now have a Z going along the surface here, right? So now what I have is a downward force, and I have horizontal forces, or what we call shear forces, along the surface. So we can break an applied force into its three components, and the three components can be produced into a resultant force or a directional force. So if I was to say, for example, draw a three-dimensional reference, just like I did, y, x, and z, and of course this is flat, but let's say our force is something out like this, that what that tells us is that we had so much x-directed force, so that comes up to the point here. We had so much y-directed force, and obviously it's a little, we had some, if we draw our z-axis out this way as well, we had some component of z. So we have components of that resultant force can be broken into some amount of y, some amount of x, and some amount of z. So what this is important to understand is that when we apply that force into the ground, we're not only applying a magnitude, but we're applying a direction. We're applying that force along a direction. The ground is going to reply with not only the magnitude, and I said this before, not only the magnitude, but the direction, the exact direction, opposite direction that we applied it. So not only the amount of force applied, but the direction of applied force, how much is in the y, how much is in the x, and how much is in the z, has an impact on how we use that force to produce human motion. Okay? So that stuff is really important to understand. The last thing, just as a point of clarification, understand that when I'm standing, right, if I'm standing on a scale, for example, and I weigh 180, 185 pounds, let's say, and I'm standing motionless, there is an acceleration, and that is the gravitational pull. I have a certain mass, and the acceleration of the Earth pulling me into its surface is creating a force. That force is measured as weight. It can be measured in pounds. It can also be measured in newtons. They're equal, obviously, or not equal. They're both units of force, and they can be, just like metric meters to inches or meters to feet, newtons to pounds, right? So, but it's important to understand my weight, my body weight downward is really applied force. And what's happening is, as I apply force down into the ground, almost all vertical in this case, the ground is pushing back with the same amount of force in the exact same direction that I'm applying my force into the ground. And that's a really important concept to understand. So this is just a basic practical guide. Force is mass of an object times its acceleration. And really, acceleration boils down to any change in velocity. Okay? And it's not only, it's a vector quantity, so it's not only has magnitude, but it has direction. That's really important. The direction part is as important, maybe more important, than the magnitude itself. And as a result of it having being a vector and having direction, we can break the components, the directional components, and the magnitude components of the force down into three dimensions and analyze how that force is being applied, and in the case of ground reaction, how that force is being applied or responded or replied back to in order to create motion itself.